Okay, so let's have a look at a few different graphing techniques. We'll start with addition of ordinates, and that's really just a pick up of our methods course. I reckon they're the 3 key points there, aren't they? There. If the two graphs have the same y coordinate, well then the resultant graph will just be twice that. If they have opposite ordinates, obviously it becomes an x-intercept. Or when one of the ordinates is 0, it's going to intersect through the opposite graph, because you're adding 0 to it. So if we remember, if we just simplify, we can write it as x cubed on x plus 2 on x. So the graph becomes y equals x squared plus 2 on x. So if we sketch both of these as accurately as we can, and there it is, nice and accurate. So obviously x squared in red, 2 on x in blue. So the key things we're looking at, let's have a look at the right hand side first. Well, obviously 2 on x is undefined. So the sum of those functions is going to remain undefined at x equal to 0. Point of intersection, you can see there it's a little bit less than 2. So we add the ordinates together, so it's sort of 1 point, well, it's going to be a little bit more, not going to quite as 4, is it? So maybe it goes about there. Okay. Obviously the x squared graph is 0 at the origin, but the 2 on x graph is undefined at the origin, so that's not of any use to us. So let's think about sort of from that point of intersection to the left and to the right. So to the right of that function, what happens? We've got the red x squared graph getting bigger and bigger, and we've got the 2 on x graph getting smaller and smaller. So if you think about the values, 2 on 2 is 1, 2 on 3 is 2/3, 2 on 4 is a half, as opposed to 2 squared, which is 4, 3 squared, which is 9. So we get 4 plus 1, which is 5. So we know that point will go specifically through 5 at 3. So we get 9 plus 2/3 is 9 and 2/3. So there's a 9 value plus a little bit. And so really the graph is the parabola plus a little bit more from 2 on x. So it acts, because the parabola is the dominant function, it acts a lot like a parabola, and it approaches the line y equals x squared, but it never crosses the line y equals x squared. So we can call that an oblique asymptote. All right. What about to the left of the function? Same sort of thing, x squared, if x is less than, well, in here really, isn't it? That's the point 1, 1. And as soon as x becomes less than 1, we square the number, it becomes smaller, but 1 on a fraction becomes bigger. So the dominant function is our hyperbola, and it's the same sort of thing. So to the left, it sort of acts hyperbolic. To the right, it acts like a parabola. Approaching the line 2 on x, which in turn approaches the asymptote. So again, we have that vertical asymptote. All right, what about from the graph here, above the line and below the line, negative and positive, where they're equal, they cancel. We can see where they cancel is sort of close to 1, -1, maybe about there, ballpark figure. It looks like the distance from there to there is about the same as the distance from there to there, maybe a little bit further along. So we're going to get an intercept somewhere along here. What happens to the left of that intercept? Well, I've got a 2 on x graph that's negative, getting small and small. I've got an x squared graph that is big and positive, getting bigger and bigger. So I get a big number plus a negative number, so I subtract a number. So our graph is going to approach closer and closer to our parabola because we're subtracting a smaller and smaller number, never quite reaching our parabola. And down on the right hand side of that, we've got an x squared graph, which is basically becoming a small positive number being added to this big negative number. Oop, that's a little bit wayward. So same sort of thing. It's going to approach but never touch. All right. We can obviously find our points of intersections mathematically, we have to solve, obviously we've got an x-intercept, so 0 is equal to x squared plus 2 on x. X squared is equal to negative 2 on x. X cubed is equal to negative 2, so x is equal to the cube root of negative 2. So that would be my point of intersection. We could find turning points, obviously, with the knowledge we have with our derivatives. But unless it actually, maybe we should do it. I guess specifically asks, so what is the derivative of the function? Let's change our pen. Sketch the graph is such a loose description, isn't it? Get back up there. So dy dx is equal to 2x minus 2 on x squared. That look about right. X to the minus 1 minus 2 x to the minus 2. Solve it equal to 0. I get 2x is equal to 2 on x squared. So I'll get x cubed is equal to 1. So x is equal to 1. So a turning point at x equal to 1. So what I've drawn is a little bit out of whack, isn't it? So, but that's okay. So in actual fact then, I should tidy up this turning point in green. So the turning point is at x equal to 1. If x is equal to 1, I get 1 plus 2 on 1, which is 3. So we'll get the point 1, 3. Which might be about there. So to tidy it up a bit better, just trying to get my rubber, lads. So we're going to go up there like that as the turning point. That point there, maybe about there, like that. So the point 1, 3. All right. Let's have a look at a point of inflection. So the second derivative is equal to what? It's equal to 2 plus 4x to the minus 3. Solve that equal to 0. So I get 4x to the minus 3 is equal to negative 2. So I'm going to get 4 is equal to negative 2x cubed. X cubed is equal to negative 2. So x is equal to the cube root of negative 2, which is the same as my intercept. So I guess what I've drawn there is close to being right, isn't it? In the sense that it is a point of inflection at that particular point. So let's get to there. Point of inflection, but not a stationary point of inflection. Yeah, because at that point the derivative is not 0. All right. So there's our full graph, which has just appeared there on the bottom right side. So it's not bad. So a little bit out there just in the way in which we act in and through here. But the key points are labelled. That point of inflection, okay, looks more of a straight line, doesn't it? But we got that concave up into concave down look. So let's have a look at the next one. Doing the reciprocals of graphs. Okay, so what's this graph going to look like? And a lot of the graphs, look, to be honest, we have basic shape we could probably do without technology, but something like this, probably for some of the calculations, we would need technology. So let's simplify. So again, I'm going to do x squared minus 1 goes into 4x squared minus 4x plus 1. So what do we get up there? We get a 4. 4x squared minus 4 0, negative 4x minus 4x, 1 minus 4 is plus 5. So we end up with y is equal to 4, I don't know, plus 5 minus 4x over x squared minus 1. So there's our graph, if you like, there. All right. So I don't know whether I'd necessarily mess around with the ordinate side of things too much here. The line y equals 4, so it's really just going to be the graph of 5 minus 4x on x squared minus 1 with the up 4 units. So instead, let's just try and find the key points that we would normally try and find. So y-intercept, let's put x equal to 0, and I might put that in the original graph. I get 1 over negative 1, so I get the point 0, negative 1. So x-intercepts, put y equal to 0. So let's go with the original. 0 is equal to 4x squared minus 4x plus 1. Now, as soon as we have that, it means that really it's just the numerator is the only thing we're concerned about that could equal 0, yeah, because the denominator can never be 0. So if we look to factorise that, 2x, we make them both negative 1s, that looks pretty good. So we get 2x minus 1 squared, therefore we get x is equal to a half. Okay? And in fact, at x equal to a half, it's a repeated factor, we're expecting it to be a turning point. Yeah? So we get another point here, a half, 0. Let's get an axis in. All right, so what does that mean? I've got a y-intercept at, say, negative 1. And I've got a turning point at a half, 0. So I don't know whether it's a concave up or maximum or minimum yet. So we're going to have to do a little bit of work with our second derivative. So let's have a look here to see if we can find a second derivative. So I might differentiate this form of it here. So we're going to have dy dx, I might just put y dashed, is equal to derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So y dashed is equal to negative 4x squared plus 4 minus 10x, what's that in there, a minus, plus 8x squared over bottom squared, which is equal to 4x squared minus 10x plus 4. 2 at the front, I get 2x squared minus 5x plus 2. 2x and x cross multiplied with 2, 1, make them both negative. And I get 2x minus 1, x minus 2. So a turning point at a half, which we expected, and also at 2. What happens if x is 2? Might put that into the top equation up here. No, it doesn't really matter. What's 2 squared is 4, so I get 16 minus 8 plus 1 over 4 squared, which is 3. So 16 minus 8 is 8, plus 1 is 9, on 3 is 3. So I get turning point at 2, 3. So we've got a turning point at a half, 0, and another one at the point, we'll say 2, 3. All right. I guess the other big one we know about our graph is with the denominator being x squared minus 1. So let's go to the green form of the function again. We could say, well, green, I wanted this to go out. I've got y is equal to 4 plus 5 minus 4x over x minus 1, x plus 1. So what colour are we going to go with? We'll go with green will do. So I've got asymptotes at plus or minus 1, haven't I? So let's go 1, 2, 3. Not quite so far. And we're also going to have a horizontal asymptote at x equal to 4. So if you think about that one there, sorry, y equal to 4, it comes about from here. And look, if we have a look at the term that we've got here in the end, if x is a really big number, if I've got 4 times 10,000, or negative 4 times 10,000, and then add 5, it's still pretty much just 4 times 10,000. So this 5 minus 4x over x squared minus 1 behaves really pretty much like x over x squared, which is 1 on x. Yeah? So the degree of that polynomial is bigger on the denominator. So as x gets really big, that expression approaches 0. All right? And so that means that if x gets really big, positive, yeah, it's going to approach, well, I've got 4 over here, 4 plus that expression, which in turn means 4 minus. So as x gets really big, we'll go blue, a really big number, it's going to approach that asymptote from underneath. All right? And if x is a really big negative number, it's going to be 4 plus a little bit. So it's going to approach that. All right? And in fact, we know that this is an asymptote on this side. So she's going to behave a little bit like that, I would imagine, through there. I know I've got a turning point here somewhere. All right? I've just got to check the concavity of this next part of it, don't I? So at the risk of running out of room, we're going to need a second derivative. Where's y double dashed? So I'll keep to green. So y double dashed is equal to, where's my function? Y dashed. Okay, so y dashed is, where is y dashed? Y dash is down here somewhere, isn't it? It's in here. So y dashed is 4x squared minus 10x plus 4 over x squared minus 1 squared. So let's go from there. So y double dashed is equal to derivative of the top, 8x minus 10 times the bottom, x squared minus 1 squared, minus derivative of the bottom. So what's the derivative of x squared minus 1 all squared? That's equal to 2 at the front of x squared minus 1 to the 1 times 2x. So what's that? 4x times x squared minus 1 times the top, which is 4x squared minus 10x plus 4 all over the bottom, which is x squared minus 1 squared squared. So what can we do? I've got x squared minus 1, x squared minus 1, and we can make that one, instead of 4 down there, it'll be a 3. So that'll be equal to, expand, and we in reality you'd have this calculation to do on your CAS, but let's just go through it. 10x squared plus 10. So I'm going to multiply negative 4x through, so negative 16x cubed plus 40x squared minus 16x all over x squared minus 1 cubed What does that simplify down to? It should, if I just go straight to an answer here, we'll get negative 2 at the front of 4x cubed minus 15x squared plus 12x minus 5 over x squared minus 1 cubed. So, does that look all right? I've got an 8x cubed there, I've got negative, so I've got 30x squared, I should have 24x, 8x, 16x is a 24x and a 10 divided by 2. Good, that looks about right. So, there's my second derivative. So, all I'm really looking for in reality is concave up, concave down, points of inflection, those sorts of things, aren't I? So on my case, if I solve that equal to 0, it's solving the top equal to 0. So if f double dashed of x equal to 0 actually gives me x is equal to 2.85 or thereabouts. Yeah. So that's where my point of inflection is. So what is that? How does that compare to everything? So there's my turning point. So I might just make that turning point a bit lower. All right, so let's put it all together a little bit. There's our turning point. I know I've got a point of inflection there. So my concavity changes at that point. That's the only place that concavity changes. Okay, so all I need to do is get a feel for whether it's a maximum or minimum, which way it is concave. So we said that point there was at x equal to 2. If I put x equal to 2 into the second derivative, the denominator is going to be 2 minus 1, so that's positive. I get 2 cubed is 8, so I get negative 32, negative 60, so I get negative inside, sorry, that's positive 32, negative 60, positive 24, negative 5, what's that? Negative 56, so that's a negative inside, negative out the front makes it a positive. So it's a minimum value there because our second derivative is positive. So that's a minimum. There's the point of inflection there, and we come across into that add there. There's no change to the way in which the graph behaves, to say it's concave up or concave down there. Let's check the nature of the graph at, say, x equal to 0. If I put x equal to 0 into my second derivative, I'm going to get negative on the bottom. This is going to be messy. And positive on the top, so I get a negative positive 10 on top, so it's a negative. So it's concave down through there and concave down the whole way. So that means the graph is going to behave concave down the whole way. Yeah. And I know it's the whole way because there's only one point of inflection. And if I was to pick a value out here somewhere, we'd see that the graph was concave up the whole way. So absolutely messy. The second derivative calculations are probably not something you would have to do tech-free, but I think it's a good question because you've got to investigate. You know, you've got no idea. I had no idea what the graph looked like. You've just got to have a look at each of the different sections. So it's really good practice. Off you go.